All right, good afternoon, everybody. I'm on page 31 of your BC Topics review packet. Make sure you're in the right packet. I've noticed some of you getting a little mixed up with where we're at, but I'm on page 31 in our series work. So I want to talk you through another free response today. This one more heavily emphasizing Taylor and Maclaurin as opposed to those convergence tests that we talked about today. So find your way to your notes and we're going to go ahead and start this one. This was a free response question on the International AP exam a couple of years ago. So we have a Maclaurin series for F given by this summation over here. And in part A, we had a very predictable and nice request to use the ratio test to find the interval of convergence for our Maclaurin series. So a ratio test is something that I hope we're asked for, because if you can run through this a few times, it's a pretty predictable request. So we have the limit as n goes to infinity of the ratio of the next term in the sequence up here. So that would be the n plus 1 power on x divided by n plus 3, because that's what happens next after this nth term. So I'm going to take that nth term, x to the n plus 1 over n plus 3, and build the ratio of that with my current term, but I'm going to just go ahead and flip this thing over, since that's what would happen if I built my ratio. I'd need to multiply by the reciprocal. Now, based on this, I can simplify my x terms. Side note, I talked about this in yesterday's video. Let's not forget, x to the n plus 1 is the same as x to the n times x to the 1, because powers of exponents, properties of exponents allow me to decompose that. And I'm dividing that by x to the n, so you can see here when I rewrite, whoops, that's not an n to the n, but an x to the n. You can see that those x to the n terms cancel. So when I take that thought bubble and apply it over here, the x to the n's are gone, and I'm left with an x in my numerator. So my limit is involving n's, not x's, so I can take the absolute value of x out and look at the limit as n approaches infinity of n plus 2 divided by n plus 3. So thankfully in blue here, that's a limit that is not super scary. I take the equal powers on n and grab the coefficients. That limit is equal to 1. So what I have then is the absolute value of x times 1 when I simplify this stuff out. And because I'm using a ratio test and I'm trying to find convergence, I know that I'd love for that to be less than 1 in order for convergence to happen. So come down to the next line. I've got the absolute value of x less than 1, which means negative 1 is less than x is less than 1 when I drop those absolute value bars. And right now, just based on that limit that I've computed, I'm really close to an answer. All I have to do is check my endpoints, and I'll be able to determine if I should include either of those ones. So let's let x equal negative 1. We'll start with that. Let's let x equal negative 1. And we'll go back to our nth term. This is the sum then from 1 to infinity of not x to the n, but negative 1 to the n over n plus 2. And this is just a prime time example of an alternating series because of that negative 1 term up top. So the alternating series really asks me to just look at what's happening when I remove the alternating piece. So I'm going to analyze what's going on with the 1 over n plus 2 right here. And I want to ask myself, is that positive? Are all the terms positive? So 1 over n plus 2. You have to try and think through mentally what would happen if you plugged a 1 in, a 2 in, a 3 in, a 4 in. Just a side note then, if I plug a 1 in, I get 1/3. A 2 in, I get 1/4. This is really helpful to establish if the criteria are met. So are all my terms positive? Yes. Are they decreasing? Yes, because the denominators are growing. So of course the fractions are getting smaller. And then third one, does the limit as n approaches infinity head to 0? Or what do you think? Does it? It sure does. The bottom's very big. So I have all three conditions met based on the alternating series test. This thing converges at our first endpoint of -1. So I can go include that one. Then I'll go ahead and test the other side. We will let x equal +1 now. And that leads to the series from 1 to infinity of 1 over n plus 2. 1 to the n, technically, but we know that 1 to any power is just 1. So this kind of resembles some of the stuff that we talked about today in tutorials. If I've got that 1 over n plus 2, there are many ways to approach this. Oops, I forgot my sum, so go put it in there. 1 over n plus 2 is a pretty easy integral test. If I want to go that route, I can see the natural log that would kind of emerge from that. But based on some of the multiple choice we did today, you might also want to try a comparison, because you can just compare to 1 over n, which is the divergent harmonic series. And I'm quickly running out of space here. Let me scroll up to the top. If I look at that harmonic series, I can run through the limit comparison test and take my series and multiply by the reciprocal of that harmonic series, and I get a limit that's 1, which is great because that's positive and finite. So since I compared to the divergent harmonic series, that means that my series is also going to diverge by the limit comparison test, because as long as I get something positive and finite, my series will behave like the one that I compared to. So the great news is that means that I'm done with my interval of convergence way back here, because I don't want to include the positive one where I got a divergent value. So interval of convergence, another way of expressing that, I can write it up here, would be -1 included and 1 not included. All right, here we go on part B. I want to let G be defined as this composition of f of -2x. We're asked to find the first three terms in the general term for our Maclaurin for G. So I just went ahead and copied down what f was, and to find G, what I notice here is that G is just defining f at a different input. Instead of f of x, I'm asked to find f of -2x. I'm going to build a little skeleton here. The original function had x over 3 plus x squared over 4, x cubed over 5, and the general term was an x to the n over n plus 2. So what I want to do here, that's a plus ... at the end, is just take that template for our function f and compose a -2x in everywhere that there's an x, which is great. That's what I've got. I've found my first three terms and my general term. There's absolutely nothing wrong with this answer, and you can leave this as your answer if that is what you want to do. That's what I would recommend doing. Some of you are stubborn and you might want to simplify this. You would get -2x over 3 plus 4x squared over 4 minus 8x cubed over 5 plus ... that -2x to the n over n plus 2. You can see that there's even more simplifying I could do if I wanted to get rid of the 4's, but again, I want to just emphasize that if it were me, I would stop right there because I've answered the question. Okay, and finally on this exam, we're asked to take the first two terms of the Maclaurin series, or we're told that they're used to approximate f of 0.1. Given that the absolute value of the third derivative is always less than or equal to 2 for this small window, use the Lagrange error bound to show that our approximation differs from f of 0.1 by at most 1/3000th. There's a lot going on here, and the big picture is that we have to use the Lagrange error bound to show that our approximation is within 1/3000th of the true value. So just to establish like what's going on here, someone comes around and says, I bet that this original function can be approximated at 0.1 with this Maclaurin polynomial. So they're using the first two terms to show that f of 0.1 is approximately 0.1 over 3 plus 0.1 squared over 4. That's just taking the original polynomial and plugging a 0.1 into the first couple terms. Now that value is close to the true estimate, and what we're going to do is use Lagrange to show that it's actually super close, like within that fraction. So Lagrange is something that we did not have much time for. The Lagrange error bound shows that your nth remainder is within, let's see, the next derivative's value at some z quantity times the next power of x all over the next factorial. So what we are trying to show is that the remainder associated with this two-term estimate for 0.1 is bounded by this Lagrange error theory. So the trickiest part about this is this weird z notation right here. So one way we can analyze that is that that's the maximum value of the next derivative. So since we used two terms to get our estimate, our next derivative would rely on the third derivative. And maybe you can see why this quantity here has been given to us. They're basically telling us that our next derivative is bounded by 2. The maximum quantity that it can take on is 2. So this Lagrange error bound requires that we plug in something for that maximum value, and the College Board has given us a 2 right here. You can keep it in absolute value if you want. The x is 0.1, and I want to raise that to the next power. So the next power would have been a cube had we kept going up there. And I want to divide that by the next factorial. So this is super cool. 2 times 0.1 cubed over 3 factorial. That's 2, maybe times 1/10 cubed. It's easier for me to deal with fractions. Over 3 factorial, 3 times 2 times 1. We cancel those 2's. So that's like 1/3 of 1/10 cubed, or 1/3 of 1 over 10 times 10 times 10, which looks a lot like 1,000, which sure is 1 over 3,000. We have shown that our remainder must be bounded by 1 over 3,000. The remainder is at most 1 over 3,000. Happy dance, we did it. A really tough Lagrange problem. Okay, so that's it for your model problem, and I want you to do a handful of multiple choice for me, really focusing on that ratio test and then this Lagrange error bound idea. So the ones that I want you to do on the next few pages, are just 4 problems. I'd like for you to attempt number 2, number 3, number 7, and number 10, and we'll check those in tutorials. Please make sure that you actually try these 4 problems so that I can get you a stamp. I'm going to stop being so nice on stamping you guys if you're only taking notes and not trying the problems too. So that's your fair warning. Good luck, do your best, we'll debrief tomorrow.